Welcome to my experiment in artificial life, evolving ants. Using this provided ant colony system, my goal is to make these ants evolve based on a specific set of parameters and see what sort of behaviors emerge. To get started, we need to open up the ant behavior script and add some parameters for genes. The system serializable just makes it so I can easily see these values in the inspector, but I can minimize them if I want. Next, we are going to create this method to randomize the genes and apply the values to the actual variables that impact the ant's behavior. This is going to generate random genes for our first set of ants that spawn, called generation 0. Notice here we're using a random range to apply these genes, which will give us a uniform random distribution rather than a Gaussian distribution. This is to give the ants more genetic diversity to start and see how the distributions change over time. Next, we need to call this method when we spawn the ants in the ant colony script. Now when we run the simulation, you can see we have all these random values in each of the parameters. Now it's time to evolve these ants over time. The first thing to do is to determine what fitness is for these ants. Since the goal of the ants is to try to find food and bring it back to the nest, I defined fitness as how much food they were able to deliver back to the nest in their lifetime. So I created a method in the ant behavior script to add to the fitness score, and I call this method in the ant colony script each time an ant delivers food to the nest. The next thing I need to do is separate the randomization into two methods, since randomization only needs to be called at the start, but I will need to apply the genes after each round of cloning or asexual reproduction. Now I need to add this evolve population method, which sorts the ants based on fitness score and keeps the top 25% as the survivors. For now, the non-survivors will be assigned the genes of one of the survivors at random. There's no genetic mutation involved here. And here is where we call the apply genes method to make sure these new parameters are assigned to the newly cloned ants. I decided to run the simulation here and see what happens. I didn't notice this until I was looking through the recordings, but here's where we have our first very interesting emergent behavior. This is an awesome death spiral where they actually created a circular shape, which is a real phenomenon with ants. I returned to my computer after about 10 minutes and all the ants had the same parameters. So it's time to add mutations. Here are the two methods to implement gene mutations with Gaussian randomness. The math for generating the distribution is at the bottom method called Gaussian, which is called for each of the parameters, with a mutation strength variable that is set to zero point 0.1 or 10% to start. So we need to call this mutate method in the evolve population method. I then decided to make mutation strength a serialized field so that I could easily change it in the editor, because now it's time to run a couple of 20-minute long simulations to give some time for evolution to occur. I started with a generation length of 60 and a mutation strength of 10%. I have inspector windows displaying the genes of 4 different ants so you can see how they change over time. Here we have a sort of death spiral after they finish the first piece of food. As you can see, the fitness levels are staying between 0 and 2, meaning ants are returning a maximum of 2 pieces during each generation. So for my next simulation, I increased the generation length to 90 to hopefully get some more variety and fitness for each generation. Some of these ants are going up to a fitness score of 3 now, and the colony's behavior seems to be more effective. They are following these established paths until the food is gone and then looking elsewhere. We got another death spiral here, which may have something to do with this barrier, but I'm not sure if that's it. After about 20 minutes, here are the values for those 4 ants I have selected. As you can see, high move speed and high turn speed seem to be very beneficial to these ants. Next, I decided to turn up the mutation strength to 15% to see if it would have any significant change. As you can see, we have our first death spiral after finishing that first piece of food. And here we have another death spiral after the second piece of food. Around the barrier, they seem to have very chaotic behavior, but no death spiral this time. After about 20 minutes, here are the gene values. The move speeds are much higher, but the turn speeds are much lower. There also seems to be less uniformity overall with the values, which makes sense given the increased mutation strength. This concludes my experiment with evolutionary ants. Thank you for watching.